Hello everyone, I am Weixuan. Today, I will introduce our paper, Learning Audio-Visual Source Localization via False Negative Aware Contrastive Learning. We are from Australian National University, Beihang University, Shanghai AI Lab, University of Oxford, and Open Research Institute. In this work, we investigate the false negative issue in the audiovisual self-supervised learning. We validate the negative influence of false negatives on the network quality, and we propose two new approaches to suppress the potential false negative effects and enhance the discrimination ability of the model, so that audiovisual data can be correctly encoded according to their semantic correspondence. We show that our method achieves better results on several audiovisual localization benchmarks. In this work, we focus on the audiovisual learning, which is a multimodal learning task. By incorporating both audio and visual modalities, models can capture richer and more comprehensive information, leading to better overall performances in various tasks. A key aspect of audiovisual learning is the fusion of audiovisual features. This involves extracting meaningful representations of both modalities and combining them in a way that captures the inherent gradations and dependencies between the two modalities. Namely, audio and visual representations should be encoded in a unified latent space. The audiovisual learning has several tasks such as audiovisual speech recognition, audiovisual scene analysis, and audiovisual source localization. In this work, we focus on the audiovisual source localization task. Audiovisual source localization is the process of estimating the spatial localization or origin of a sound source by combining audio and visual information. As shown, if we given a visual scene and an audio wave clip, we aim to find out the objects that are sounding. We first revisit the existing solutions for this task. Various methods for audiovisual localization employ a contrastive learning framework with NCE laws. It assumes the audiovisual scenes from different videos are distinctive. The audiovisual scene treating paired audio and visual image samples as positives and samples from other pairs as negatives. The objective is to maximize the similarities between the audiovisual representations from the same pair and minimize the similarities between the different pairs. However, false negatives can arise when similar audio or visual samples are presented. Enforcing smaller similarities between these features may confuse model training and result in low-quality representations. As shown in the right figure, since no manual class labels are available, two clips with similar semantic class will be wrongly pushed apart in the feature space. Such an issue is more prominent in audiovisual learning since the class number of audios are limited, for example, 309 classes in VGG-Sound dataset. So if we increase batch size, we inevitably will encounter false negative problems. We conduct a pilot experiment to investigate this issue. So by manually substituting true negatives with false negatives in the training samples, we observe a significant decline in the audiovisual localization performances, indicating that the model is confused by these similar samples. This experiment highlights the substantial impact of the false negatives on the model quality. To address such an issue, we propose FNAC, False Negative Aware Contrastive Learning. It has two complementary methods, FNS, False Negative Suppression, and TNE, True Negative Enhancement, to address this issue. To suppress the false negative effects, first, we need to detect potential false negatives. We propose to leverage the unimodal feature representations to calculate pairwise sample similarities, so-called adjacency matrix. As shown in the figure, for audio features, we calculated self-correlation matrix using dot product to obtain their intra-modal adjacency matrix. Likewise, we do it on the visual features. Such similarity matrices assist explore potential semantically similar samples. Second, to suppress the false negative effects, we propose to impose intra-modal adjacency as a software supervision signal for inter-modal contrastive learning. We directly regularize the distance between the multimodal simulating matrices and the contrastive matrices, as shown in the equation below. In practice, we calculate L1 distance. Such a regularizing term is a parameter-free process, so the false negative effects can be adaptively regularized. Second, we introduce TNE. To further reduce the misleading effect of false negatives, we turn back to its core concept, which is if two objects look similar, their corresponding sound should also be similar, and vice versa. Specifically, we localize the sound source objects by paired audiovisual samples, pop up their original visual features, and encourage those of true negative samples to be pulled away. The process is called true negative enhancement. As shown in the figure, we get adjacency matrices of audio and foreground visual features respectively and regularize their element-wise distance. It encourages the model to focus on different pixels to mine discriminative visual features according to the audio similarities. In summary, we suppress potential false negative issues and enhance model discrimination ability. Both methods can be seamlessly integrated with the existing contrastive learning framework as extra regularization loss terms, as shown in the equation. We conduct thorough experiments on 4 benchmarks: Flickr, VGG-SS, heard, unheard, and AVSBench under different settings and different training data. We show great results on all these benchmarks and outperform previous methods. Finally, I want to show you an interesting observation. We show quantitative and schematic analysis of the false negative mining ability of our method. Intuitively, a good audiovisual model should be able to generate similar visual representations for the same class. To validate this intuition, we construct a batch where all samples belong to the same class. As shown, baseline method only highlights a diagonal since each audio feature is only like the paired image feature, while all others are dissimilar despite that they are from the same class. While the similarity distribution of our matrix is more evenly spread as most of the samples are regarded as similar. It indicates that FNAC has implicitly learned semantically aware feature and clustered them in the latent space. So false negatives will be effectively identified as they are closer in terms of the feature distance. That's it for our work. Thank you, and please visit our code and paper